Hello everyone, my name is Rajesh. I'm with Team ALOW, and today we are going to do a presentation on risk analysis of Bailey's Place retaining wall.
My name is Gabriela Lara, and I'm presenting with Team ALOW.
Yes, my name is Kevin O'Shea, and I will be presenting with Team ALOW.
And I am Molly Waddell, representing the W portion of Team ALOW.
To introduce our risk management plan, we'll be starting off with the project scope, led by Kevin, and the cost estimate and schedule, led by me, Gabriela.
The project scope is to reconstruct a 148-foot retaining wall with an elevation ranging in height from roughly 10 foot to 18 foot. There will also be some construction of a water main, street lighting, and roadway and traffic work. The location of the retaining wall will be between Bailey Avenue and Fort Independence Street in the borough of the Bronx, New York. The limits of the project are from Bailey Place, Bailey Avenue, and West 234th Street to approximately 150 feet north. The project is designed in a staged construction area to minimize disruption to existing utilities.
The estimate calculated for this project is based off the standard specifications published by the New York City Department of Transportation and Department of Environmental Protection. The items in this publication are a unit price method basis, which include labor, equipment, material, and services within a single line item. This table provides a general breakdown of the project costs in terms of major components. The bulk of the project costs can be attributed to the retaining wall and the trunk main and distribution mains. This histogram shows the cost of the entire project after each iteration of risk analysis performed by the program, resulting in a few values of note. There is an 80% chance of the project being completed below $6.218 million, about 7% more than the design estimate. The program also generated a 50% chance of completing the project below $5.978 million, about 3% more than the design estimate. The project start date is March 28, 2016, and is scheduled to complete on May 13, 2018. The project's total duration is initially computed to be 535 days, or approximately 18 months. Due to one task, tree planting and related work, having a start date fixed to the beginning of spring, the actual span of the project would be 746 days, or about 24 months. This also causes all other tasks to have float leading up to this one, and makes it the critical path. This diagram also presents some notable results. There is a 80% chance of the project being completed under 774 days, about 4% more than estimated. The program also generated a 50% chance of the project being completed in under 753 days, about 1% more than estimated.
The next area we're going to talk about is the risk management procedure. Within the risk management procedure, it consists of the risk identification, risk analysis, qualitative risk analysis, and quantitative risk analysis.
Thanks, Kevin. The first step in the risk management procedure, risk identification, allows us as risk analysts to proactively take a look at the risks involved in the project. Influence diagrams are a visual representation between our project's risks and allow us to get a better understanding of the relationship between the risks. For the purposes of our project, we separated our influence diagrams into 4 outcomes: change orders, construction damage, compromising of worker safety, and scheduling construction delays. Here, we'll take a look at one of our 4 influence diagrams, the diagram representing construction damage. It can be seen that there are many risks which could lead to the possibility of construction damage. The association between the risks is very much up to personal judgment, but our group determined that our diagram would represent 14 uncertainties, seen as red ellipses, and 1 decision event, represented by the green rectangle, which have the potential to cause construction damage, which is seen in the blue diamond. Any given risk can also impact the outcome in multiple ways. Using this diagram as an example, we see that the faulty equipment located midway on the left-hand side can directly cause construction damage, or it can indirectly cause construction damage by leading to improper alignment of the prefabricated trunk main.
Thank you, Molly. The risk analysis that we performed was both qualitative and quantitative. Qualitative risk analysis is a project management technique that deals with discovering the probability of a risk event occurring and the impact the risk will have if it does occur, using a variety of subjective and judgmental techniques to rank and prioritize the risks. Each risk has been assigned a qualitative probabilistic value that it is going to occur, and also a qualitative value for the project impact on its cost, scope, schedule, and performance. The analysis where the risks are classified into uh, very low, low, medium, high, and very high scales. Risk register is used to calculate the risk score, and quantitatively analyzing the risk associated with the project involved estimating the risk in terms of frequency or probability of a loss to make the appropriate decisions. In using approach, exposure assessment was critical. Each hazard had to be quantified in terms of both duration and cost.
Using the Primavera software, we developed a risk register as a way of performing our qualitative risk analysis. This allowed us to get a high-level understanding of our risks and impacts, as well as see the links between the risks and their corresponding schedule, tasks, and costs. Risks were evaluated based on probability, scheduling, cost, and performance, all of which are factored into the score which is associated with the risk. We see here a portion of our risk register which shows our assessment of the first 10 of our risks. Some of the values assigned to the risk have numerical values shown as percentages, and these are risks for which we've performed further quantitative risk analysis and will be discussed later in the presentation. Here we can see our generated risk matrix, which shows the relationship between risks and tasks and their corresponding impacts. Our report only involved linking 12 of the chosen risks to the appropriate schedule tasks, but it can be seen that the risks varied in both impact level and probability of occurring. We will now go into further detail on the quantitative analysis performed on 12 of our selected risks. Each member of Team ALOW will describe 3 risks, beginning with Gabriella.
Planning for archaeological findings would necessitate being aware of governing regulations that preside the project site. Initial studies performed beforehand incorporate regional and historical and site-specific information with the analysis of historic maps, determining whether or not any significant buried historic remains may be uncovered during the project. The mitigation response chosen for this risk was accept, since archaeological resource regulations must be followed if they apply to the project site. The investigations mentioned beforehand may incur a cost of approximately $20,000. Monitoring of this risk can be done through educating construction laborers and supervisors on key indicators to be aware of during excavation that may be of archaeological importance. Controlling this risk once it's set in motion by encountering archaeological resources must be done by hiring archaeologists to perform the necessary monitoring, fieldwork, and testing. Costs incurred by this type of risk are assumed to be $60,000 with a scheduling addition of about 27 days. Reporting procedures during mitigation are also determined by regulating agencies and should be performed by archaeologists hired. Mitigation is typically a full archaeological excavation of the project area, which occurs only when all the other steps indicate that a major archaeologically significant site remains beneath the project area. Soil conditions not captured by exploration performed during the design phase substantially impact the project. Our main component, the retaining wall, could suffer substantial design changes. Sewers and water mains may need to be designed differently as well. This could be changes in grading or the foundation of the pipes themselves. Excavations may have to be adapted to conform to the new soil conditions. To plan for this risk, the responses are expected to be accepted. Since geotechnical conditions are crucial to this type of construction, engineers must communicate to contractors the specifics and severity of geotechnical design. To monitor this risk, inspectors should be aware during excavations of any significant soil changes that vary significantly from expected conditions. If deviations were to arise, this risk can be controlled by performing the necessary investigations to adjust the design to be executed. Mitigating actions were considered as follows. Performing additional subsurface investigations would cost about $10,000 due to its supplementary nature in respect to the investigations performed during design. Revising the geotechnical design of the temporary support system and the permanent retaining wall was estimated to be $20,000, since excavation support systems and retaining walls tend to be tailor-made to site conditions, so extensive design review may be needed. Revising distribution main and trunk main foundation design would cost about $10,000, since many design standards exist for these type of foundations, which are created by governing agencies, so extensive funds would not be needed for this response type. The actual project costs are expected to be quite significant, about $285,000 in additional costs to the project, and an additional 28 days were expected to be scheduled. Out-of-scope work, which in turn produces change orders, may cause alterations to the budget, timeline, or both. Planning for this risk warranted accept-type responses, since change orders are a fact of virtually all large-scale projects. Some change orders can be avoided, but the chances of not encountering a single change order on this sort of project is almost zero. Construction managers should be aware of the process this entails, and proper execution of this task. Monitoring for this risk requires extensive experience, coupled with thorough knowledge of the project and construction procedures on behalf of construction supervisors. Although change orders cannot be avoided, this may allow for some to be circumvented. The controlling mitigation action assumed for change order processes typically do not incur devastating costs. $10,000 in 7 days were allocated for this measure. However, change orders can affect any given task within the project, so a high cost was associated with its occurrence, $255,000. Schedule implications are of approximately 28 days.
Common scheduling errors can be caused due to many reasons, such as errors in technical logics, overlooking procurement of critical materials, or sometimes failure to consider physical, weather, or resource constraints. Sometimes it could also happen due to unrealistic productivity or durations. And keeping in that mind, we have given a 40% probability of this risk to happen. And the response we choose to go with is reducing the risk. That can be achieved by a mitigation strategy of employing a scheduling consultant. And for that, the mitigation cost would be $200,000. This mitigation strategy would reduce the impact on cost due to this risk from $471,000 to $76,500. And the schedule impact can be reduced from 394 days to 195 days. Material delivery delays. Delays are extremely common on the construction sites. Unforeseen delays may be mainly due to accidents and bad weather. Late delivery results in workers staying idle on site, which eventually results in no work progress. And to compensate the work progress, they have to work overtime, which results in loss of productivity. Thus, this risk was given a very high impact rating in terms of cost, and it was given a 40% probability rating to occur. And the response we chose to go is to reduce the risk. This can be achieved by applying mitigation strategy of applying material logistics, a shipment tracking based approach to provide inventory transparency, and a proactive material delivery approach for timely material availability. This mitigation would require a mitigation cost of $100,000, and this mitigation would reduce the risk impact on cost from $900,000 to $52,500. And the schedule impact can be reduced from 337 days to 166 days. Improper coordination with utilities. Utility delays are one of the primary reasons for increased costs and schedule delays during the construction phase of a project. Although there is a low probability for this risk to happen, if it happens, there is a very high impact on both the schedule and cost of the project. The risk response is to reduce the risk. This can be achieved by hiring an expert consultant who has a very good knowledge on dealing with the utility works. For this mitigation strategy, the mitigation cost is $200,000. This mitigation would reduce the cost impact from $964,000 to $82,400. And the cost impact due to this risk can be reduced from 284 days to 122 days.
Thank you, Rajesh. The first risk that I'm going to talk about is utilities for nearby existing buildings may be disturbed or damaged. Utilities such as electrical lines, sewer lines, pipes, conduits, anything that is below or above grade, if it's not properly located during pre-construction field walkthroughs or surveys, they could be damaged or disturbed in any way. So this is why we have a high probability for this one, and this could affect the schedule and the cost in a high way, especially with these utilities if they're seriously damaged. Um, this could really drive the cost up and cause a delay to the project. So proper field surveys before construction and utilizing field markers to allow everyone to know where these utilities are below grade helps make everyone aware. Also, proper site meetings and coordination meetings will keep everyone on the same page, especially with utilities above ground having proper supports. Just an extra support goes a long way during excavation might cause a ground movement or something. Having extra materials on site in case a pipeline or a conduit is disturbed or damaged just will save a lot of time and won't severely affect the schedule. Also, having readily available contractors there to do the work that won't take away from the actual work on the project is a huge help. The next risk I'm going to talk about is weather-related delays. Bad and unpredictable weather can cause delays to projects. Weather is the most unpredictable risk when it comes to a project. The weather could be nice one day, and then within the next couple of hours, the weather could be very lousy, and it's so unpredictable. You don't know how the weather's going to be that day. So this is why there's such high probability for this risk. Ways to mitigate it and avoid it: having extra float within the schedule throughout the year to allow yourself time and just ways to adjust if one day you know it's going to be bad weather, well, then you could have another task that you could complete. Also, having extra money in case bad weather does occur, and you say you have a crane on site one day and you need the crane 2 more days, so you were paying an extra day or two for the crane. Having money in the budget will allow for this. Also, multitasking. Like I said before, if you can't complete one task this day, well, have another task lined up right behind it so that it won't cause any delay to the schedule. This is a risk that we will accept, and constant communication among all parties every day when you know the weather is going to be bad will help to avoid a lot of problems, and just constant review with the project team to make sure that you have another task that can be completed if your scheduled task for that day cannot be. The last risk that I'm going to talk about is damage to nearby structures. Structures that are close by can be damaged during construction. Construction activities such as jackhammering or excavation, which would cause a fault in the ground, can cause damage to buildings nearby, to crack, or anything bad, something can happen. So the probability for this is medium because we provide all the support to make sure that this does not occur. So some things that we could do ahead of time are proper shoring when you're excavating to make sure no landslides, or especially with a retaining wall, nothing collapses and causes any movement in the ground which could fracture a piece of the building nearby. Extra supports and bracing is just more support, and it helps to strengthen the structure that you're working on. So for this retaining wall, proper shoring and bracing really will help strengthen it to avoid these damages to the nearby structures. If we do have problems, we will transfer this risk to insurance companies who will deal with this. Other ways we can deal with it is have extra materials on site so we could fix this structure as best as we can until the insurance companies deal with it down the road. And also constant communication, allowing the structures or buildings nearby to know when we are doing excavation so they know to be aware and really for their safety. Alright, thank you. Those are my 3 risks, and Molly is up next to discuss her 3 risks.
Wrapping up on our chosen risks, I'll begin with changes in initial design. A design change can occur for many different reasons, often as a result of another risk occurring. Because of varying probability of the risks which could lead to a change in design and our experience in past projects, we've given a medium probability of 40% to this risk. The response for this type of risk was classified as accept because any changes to the design cannot be avoided or transferred, and they must be incorporated into the project by the team. Our mitigation strategy for this risk involves the creation of a sub-team, which will review the project design and make sure it meets all of the project requirements, with the hope that any shortcomings will be recognized early on and will lessen the likelihood the design needs to be changed. The team will also handle any reporting of the risks, as this would be included in the review and documentation of the change of the design. This team will consist of project staff and will not add any significant cost to our project. Moving on to the risk of security breach, which is given a high probability of 60%. The reason for this high probability is due to our site's location in a very urban area near roadways and with a heavy volume of people near the site on a daily basis. As a precaution for the risk of security breach, fencing can be installed around the project site to deter people from entering. Additionally, lighting can be installed to make the area more visible and less appealing to those who would wish to access the site illegally. The mitigation response for this risk is that of accept, because once the site has been broken into, the risk will have occurred and there's really no way of lessening that fact. We can, however, set up mitigation actions such as hiring on-site security to monitor the area, as well as installing additional fencing. These actions would apply to the construction phase of the project, and the total cost is estimated to be $255,000. The last risk I will address is the risk that there is pressure to expedite the project. This pressure can be from the project owner, from government, or from other authorities, and we've given it a medium probability of 40% based on the rate of seeing this occur in past projects. A response of accept is because often the pressure is occurring from a higher authority and is not something which can be challenged, meaning it must be carried out and accepted. Luckily, we can set up mitigation actions to take this risk into consideration. We've budgeted $200,000 for the hiring of additional staff to join the project in order to accommodate the increased workload and to manage this expedited project timeline. Additionally, the creation of a sub-team from existing project team members will serve as a communication tool to keep the higher authorities who are putting on this pressure well informed of the progress, and will keep them updated on the project status. That concludes the analysis of our 12 focus risks. I'll now hand things over to Rajesh, who will cover the risk report generation, including a comparison of our pre- and post-mitigated results.
In this schedule analysis, you can see that if we go in a deterministic way, that is without giving the uncertainty values for the project, you can only be 13% confident that you can finish the project by 13th of April 2018. But after you input all the uncertainty values, you can be 80% confident that you can finish the project by 20th of September 2019. Well, in terms of duration, with all the risks involved in the project, you can only be 13% confident that you can finish this project in a duration of 748 days. And you can be 80% confident that you can finish this project in a duration of 1273 days. Well, in terms of cost, with all the risks involved, you can only be 3% confident that you can finish this project with a $5.7 million budget. And you can be 80% confident that you can finish this project with $7.7 million budget. After the risks are mitigated, you can be 80% confident that you can finish the project by 8th of January 2019. Well, before the mitigation, the finish date was 20th of September 2019. After the risks are mitigated, there is an 80% chance to complete this project in 10-18 days. The pre-mitigated PAT duration was 1273, which upon mitigation was brought down to 10-18 days. You can see that there is an 80% chance that this project can be completed with a budget of $8 million. Before the mitigation, it was $7.7 million. Although there is a difference of $300,000 between the PATs of pre-mitigation and post-mitigation, without having the risk mitigation done, the owner will have no idea how the cash flowings will vary during the construction of the project.
Thank you for watching Team ALOW's presentation. If you have any questions, please email us at the following emails listed below.